So we need to understand the nature of light. So light is a form of electromagnetic radiation. It's a form of energy. It's composed of two perpendicular waves. These waves oscillate, meaning they go up and down. There's an electric field and a magnetic field, and they move together, but they're oscillating in perpendicular directions. So an electric field is a region where an electrically charged particle experiences a force. A magnetic field is where a magnetized particle would experience a force. So all electromagnetic waves move through space at the same constant speed. We call it the speed of light because it's the speed at which light moves. The speed of light is 3.00 times 10 to the 8th meters per second. So it's very, very fast. We're going to do an experiment, experiment 7A, and there's going to be a question in there that's going to ask you to take some different colors of light and order them by their speed. That is a trick question. Because which moves faster, red light or green light? They all move at the same speed, the speed of light. Okay, so I just told you the answer to that one. I'm expecting you to all get it correct. Here's an illustration of electromagnetic radiation. So here we have the electric field component. It's oscillating, and the magnetic field component is oscillating in this perpendicular plane. But they're moving together at the same speed. So here we have an illustration of lightning striking something down here. So we see the light, and we don't hear the crack of the thunder at the same time, right? That's because sound moves significantly slower than light does. The light comes very quickly. The sound takes longer. So light moves at the speed of 3 times 10 to the 8th meters per second. Sound travels around 340 meters per second. So we see the light, and then later we hear the sound. And that's why you can estimate how far away the storm is by measuring or counting, estimating the time difference between when you see the flash of lightning and when you hear the thunder. The farther away it is, the longer that delay, and it's because of the different speeds at which those two things move. So there are several things that we use to characterize waves. So this is a sine wave, and we can characterize it in different ways. We can look at the amplitude, how high it is. This is the distance from a node, which is where it crosses zero, to the highest point of a crest or a trough. So that distance is the amplitude. Amplitude in light measures the intensity of the light, how bright it is. Larger amplitude, brighter light. We also measure the wavelength, which would be from one crest to the next crest. That's the length of the wave, so we call it the wavelength, and it's got the Greek symbol lambda, which is a little bit like an upside down lowercase y. The wavelength, different wavelengths we perceive as different colors. So here, red light has a longer wavelength than yellow light, and blue light has an even shorter wavelength. So the wavelength determines the different colors of visible light. The amplitude is how bright or dim the light is. So right now, the light coming from the overhead lights is lower in amplitude because I dimmed the light so we could see those videos a little better. We can also look at the frequency. And the frequency is given the symbol nu, which looks unfortunately like a lowercase v, but it's got a slight curve there. The frequency is how many waves pass a point in a given period of time. So the number of waves or the number of cycles. And so the unit of frequency is cycles per second, or just per second, how many per second. And that's given, that's called a hertz. So Hz is a hertz. A hertz is one cycle per second. The total energy of the light is proportional to the amplitude, how tall the waves are, and the frequency. The larger the amplitude, the more force it has. The more frequently the waves strike, the more total force there is. So ocean waves are not light, but thinking about standing in the surf at the beach, that can help us to remember some of the relationships between these things with light waves. So, I'm at the ocean and the surf is low, right? The waves aren't very tall. And so I'm standing there and they're crashing on me and it's all nice, right? But if the surf was really high, now these waves would probably knock me over, right? There's more energy in them. They're hitting with more force. So higher amplitude, more energy, more force. We can also talk about the frequency. So it's important to remember that light always moves at the same speed, but the frequency can be different. So we could have a low frequency. So I'm standing there and every minute a wave hits me. Or I could be standing there and a wave is hitting me every 30 seconds or so. Which one is going to give me more of a pounding? The one where I'm getting hit more frequently, right? Bang, bang, bang. I'm going to get tired of that after a while. So more force, more energy when the frequency is higher. So when waves are traveling at the same speed, which light waves are, a shorter wavelength means a higher frequency. So again, I'll draw some of my very ugly waves. So if these waves are traveling at the same speed, these waves are going to hit me less frequently than these. The frequency is how many waves hit me per second. So the wavelength and the frequency of electromagnetic waves is inversely relational. If you have a high frequency, you have a low wavelength. So this is going to have a higher frequency. We see that the wavelength is shorter. Here the wavelength is longer, and so it's a lower frequency. The speed is constant, and so the wavelength and the frequency are related by this relationship. The frequency is equal to the speed of light divided by the wavelength. The color of light is determined by its wavelength, which is related to its frequency. So if we pass white light through a prism, the light will get bent differently because of the different wavelengths, and so we can separate what appears white into the different colors. So white light is a mixture of all the colors of visible light. It's a spectrum, it's continuous. The colors present in the rainbow, or invisible light, are red, orange, yellow, green, blue, indigo, violet. One way to remember that order is Roy G. Biv. Like somebody's really weird name, Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. The colors of the rainbow are always in that same order because those colors are from different wavelengths, and wavelengths get bent according to how long the wavelength is. So what we perceive as color, so here we have a picture of a woman wearing a red shirt. Her shirt appears red to us because that fabric is absorbing most of the colors of the light, but it's reflecting the red light. So as white light hits her shirt, much of it gets absorbed, but the red frequencies are reflected. So what we see is red light coming off of the shirt, and our eyes perceive that. So we could do some calculations like this. A laser dazzles the audience in a rock concert by emitting green light with a wavelength of 515 nanometers. Calculate the frequency of the light. So the wavelength is 515 nanometers. The frequency, we had that equation, frequency is equal to the speed of light divided by the wavelength. The speed of light, and I will give you that on an exam if you need it, 3 times 10 to the 8th meters per second. So I've got the speed of light and I've got the wavelength, so I can just plug those into this equation. Are the units going to work out? No. What I want is 1/2. That's a hertz. That's the unit of frequency. But my meters and my nanometers are not going to cancel out. So I could do a separate calculation where I convert nanometers to meters. I want to show you a shortcut. What does nano mean? 10 to the minus 9. So n stands for 10 to the minus 9. So here, instead of writing n, I'm going to write 10 to the minus 9. So I'm going to erase this. And where the nanometer was, I'm going to write its mathematical meaning, and then the meter stays there. This is not proper scientific notation. Your calculator doesn't care. You can still do this. Now the meters cancel out. And so my unit is going to be 1/2. So we got 3 times 10 to the 8th divided by 515 times 10 to the minus 9. 5.83 times 10 to the 14th cycles per second. It's a really big number. Light moves very fast, and the wavelength is really short, so we expect a large number there. Any questions? Yeah. That's a 1/s. Yep. It's 5.83 times 10 to the 14 per second. It's also sometimes written as s to the minus 1, or hertz. Any other questions?